You heard I gave 3 talks about quantum spectrum, but it's a different quantum spectrum, so it's nothing in common. Yeah. So I want to compare kind of 2 stories. Yeah, first story will be think our ABC epsilon or D story with Jan. Kind of first reminder on ABCD epsilon with Jan Söbelmann. So it was the only paper which we wrote in the subject. So I will come with kind of simplified setup. So what is it? I have a complex curve, smooth, compact, complex curve. Of some genus G. And this curve is embedded to, maybe say, germ of a complex surface S over complex numbers, and the surface has also holomorphic 2 form, symplectic 2 form. So obviously curve is Lagrangian. Okay. Now one can try to assume this genus is bigger than 0. Now I can try to move the curve. So the curve will be kind of depending on some parameter b. It will be point b0, and b0 will be some parameter space. You get germ of some parameter space, and the basic fact is this b is smooth of dimension is equal to genus of my curve, and the tangent space is global 1 forms. Okay. So you get this G-dimensional family of curves, and then on B we have variation of hot structures, or maybe say polarized hot structures. Namely, for each point B you get, we consider cohomology, first cohomology of corresponding curve, sigma B. It's C to G. It's isomorphic to C multiplied by, it has a lattice with symplectic form, and contains first term in Hodge filtration F1. H1 is its global holomorphic omega 1 CB, which is amorphic CG. You get subspace which of middle dimension, and because it has pairing, it will be Lagrangian subspace. So it means that for each point, and locally cohomology of my thing stays the same. It's just the same vector space, and I have moving Lagrangian subspace here. Again, claim there exists unique up to shift map, it will be holomorphic embedding of my this G-dimension manifold to C2G, which will be cohomology of my curve, embedding whatever phi, such that tangent, if you consider tangent map of this phi at point B and apply to local embedding, yes, it's germ. Everything is a germ.
No, but say somewhere it's local. Because B is a
Germ, yeah, it's a germ. Yeah, it's all local, and all cohomology I identify because it's a small germs, they have a flat connection. And if consider of gamma sigma B of tangent space, it will be equal to the embedding because tangent space is equal to global one forms, and it's embedded to H1 of sigma BC, which is isomorphic to this guy. So this diagram is commutative. Yeah, so automatically what you get affine symplectic space and kind of curved submanifold. B will be a curved Lagrangian submanifold in affine space. Germ of Lagrangian submanifold in affine symplectic space. Okay. Yeah, so that's basic geometry. We get this embedding. What people really do, they choose a splitting of this symplectic lattice into A cycles and B cycles. So you get also get some kind of lattice points here. You split kind of A cycles and B cycles or dual guys. Then it will be graph of differential of some function, and B will be a graph of differential of some function of G variables. And these functions people denote F0. It's prepotential. Yeah, so this F0 is a function on affine G-dimensional space with integer kind of coordinates. It describes the whole geometry of this modular space. The story is that it's secretly here we speak about some three-dimensional Calabi-Yau, because when we have a surface, a curve in a surface, it's given by some equation. Like surface is given by equation, some function. Let's say xy will be coordinates on the surface is equal to 0. Then we can write f of xy plus uv is equal to 0. We get add two more variables. We get a three-dimensional non-compact manifold with holomorphic volume element, and this will be family of such three-dimensional Calabi-Yau threefolds. And secretly we're speaking about variation of chord structure in H3 of these guys, not H1. But this H3 is reduced to H1 in this case. So it's a remark. So it's in all this topological recursion, it's about special classes of non-compact Calabi-Yau threefold which reduce to curves. Okay, so you get this variation of chord structure. And what is the result of topological recursion, at least one of results? We quantize B, quantization of B of form power series in the following sense. We have affine symplectic space, and on this affine symplectic space on any affine symplectic space, I just denoted stupidly S to G, but up to affine. The construction is invariant under affine transformation. You get canonical sheaf of algebras coming from star product. You get locally defined notion of algebras over form a power series in H bar. So what really goes to in coordinates? You can see this sheaf of algebras vector space will be usual functions series in H bar with values in functions. It will be as vector space. It will be O of this C2G H bar, but the product is Moyal product. Yeah, maybe I just remove. I recall you what is Moyal product. You write F cross G will be sum over n greater than 0, 1 H bar to power n over n factorial, and we take sum over I1 In J1 Jn, which are the coordinates in my C2G. I take omega y I J1 omega coefficients of symplectic form, and take di1 din of f multiplied by dg1 dgn of g. This is a formula for the star product. It's invariant under covariant invariant under respect to affine transformation preserving symplectic form. And here in my talk I use kind of mathematician's H bar without I. Yeah, because this unitarity will play no role for my thing, so I don't need imaginary numbers. Okay. Yeah, so it's whole thing is periodic algebraic, or any field characteristic 0. Yeah, so I get the star product, and
when you do Moyal product on C infinity functions, you would have d bar differentiation.
yes, but here it will be holomorphic function. I get holomorphic objects and nothing to do. And now I get this sheaf of algebras, and if I have this this kind of quantum sheaf mod out by H bar, I get usual functions, and here I get a sheaf of ideals of sheaf of my B Ct in C2n C2G. And what is the quantization? You leave this sheaf of ideals to you get flat deformation of the sheaf of ideals to over H bar. So you get kind of a classical, and quantization definition, you some quantum ideal sheaf in ideals, which is flat over kind of doesn't change size over CH bar, and mod H bar is equal to classical ideal. Okay, yeah, it's some abstract definition. This will be result of topological recursion. What does it mean, kind of in concrete terms? Concretely, it means the following. You choose again, pick a splitting of coordinates in A-B cycles. Splitting kind of A-B cycles. So this B will be graph of some function of maybe variables I denote like Q1, Qg. Will be coordinates on this cycles, and when you get this ideal, it will be ideal of expressions which kill certain function. You imagine that you consider things like this. If you imagine such formal expression where f0, f1, f2 are other functions of Q1, Qg, and if we get such guy, yeah, so in topological recursion I'll put 2 to power 2 minus 2g, it will be like square of string coupling constant in or in square in matrix models. yeah, so this guy is killed by some by something. It will be ideal what kills this story, but this f1 f2 are defined up to constant, because if you add a constant, you multiply by this expression h bar, so it will be killed by the same story. So what really happens, you have df1, df2, df3, get infinite sequence of closed form on your Jeromov manifold of your split sequence. So you get this quantization. If you choose split coordinates, is the same. So it will be closed one form on q1, qg variables, and maybe you take series in h bar. That's what you add here. Series h bar. It will be freedom parameters specifying what does mean quantization. Okay, that's things which you should remember. So this, if you split coordinates, it's just give it's equivalent to kind of formally move your Lagrangian manifold. But if you change coordinates, it will be some kind of more tricky correspondence. Yeah, but that's.
So the fact that IQ is a flat deformation over C power series in H bar, is that enough to uniquely determine it?
Yes, it's exactly this ideals. If you choose the splitting of coordinates, exactly the sequence, exactly these functions.
Okay.
It's the same story. Yeah.
What happened to the non-perturbative corrections?
Later. No. I was speaking about form power series. My talk. Yeah, it'll be all essentially form. It will be a little about this non-perturbative collection.
Could you just recall the definition, the formal definition? I couldn't.
Definition of what?
Of this IQ.
As a definition of IQ is an annihilator of this function. If you get this function,
So it's like a choice of this f1, f2?
yeah, it's a choice of f1, f2 gives the ideal. And conversely, ideal is this choice of f1, f2, but f1, f2 defined up to constant, so it's really, only derivatives of these guys. Yeah, so this set of ideals is the same as this quantum ideals. It's a set of choices. Okay, now how we constructed this from, I just recall this topological recursion business. Construction of quantization of this, one can say this wave function. Via topological recursion, it goes through some the following thing. You put some kind of make additional choice, which is choice. You can see the holomorphic foliation of my surface, one-dimensional foliation of surface. So it means that it will be kind of like this, and I get my curve sigma, and assumption is sigma touch leaves only minimal way, just only quadratically. So you get this ramification points. So in real life example, this surface will be cotangent bundle to some base curve, and foliations are vertical shifts, and then. But I can want to, in my talk, just to really specify what is really needed. I don't need cotangent bundle, I really need only foliation in this thing. And how we can proceed. So we have this various ramification points, which are points when this touch, get finite number of touching points, which are ramification points. to denote A, as Bertrand denote yesterday. And what I do, I kind of make local coordinates. I remove, I make a small circle on the base of these things and remove corresponding things on the circle, remove disks, which say something like x, if my horizontal coordinates is equal to epsilon, is maybe projection of my locally I have like coordinates x and y, and ramification along, so local coordinates will be x and y, and I take x minus xa, because coordinate a x of point A should be less than epsilon. I remove the small circles, and here it will be double cover because of quadratic story. And I get surface with boundary. With boundary, it should be just union of circles, or a copy of circles, which are double cover of this circle. So I get bunch of circles, and outside my surface is transversal to affiliation. And when I have a Lagrangian affiliation, it's automatically Lagrangian. Leaves have a fine structure. I kind of now start to move my surface such that inside S, my Riemann surface is boundary, such that the boundary projects kind of 2 to 1 again to this union of circles. Now, when I try to move these things, I get certain huge infinite dimensional space, affine space, because I consider holomorphic sections of affine bundle. Get infinite dimensional affine space. This affine space, now I can consider moves not of surface, but just move this boundary circles. When I move boundary circles, movement of boundary circles, for each circle, I have a property that integral of this to form of the disk surrounding the circle is to 0. This kind of constraint, that integral of to form of a disk bounding circle is 0, some constraint. I map to some huge space which will be something like C infinity of product of C infinity of one forms on circle with a residue equal to 0. Yeah, you can mark also, so you can consider this for each circle you get space of like a series in one variable. This one forms, and this for this one forms you have canonical symplectic pairing because it will be differential of some d minus 1 of alpha, and pairing between these two forms will be integral of d minus 1 of alpha wedge beta of this one. It's well defined because residue is 0, so you get product of symplectic affine spaces, and this guy will be coisotropic, and this is symplectic. So you get infinite dimensional symplectic space, you get coisotropic subspace, but then you get also interesting, very nice Lagrangian submanifold in this affine space, namely things which bound disks from inside. This is the same space, which bound disks, and this is Lagrangian, and it's given by quadratic equation, and then this ABCD tensor gives you canonical quantization of this guy. Yeah, so get this thing's quantization of huge Lagrangian subspace in infinite dimension, and now by coisotropic we call it straight You can immediately go to quantizations you can play the same things with ideals, and you get quantization of this Hamiltonian reduction should be my finite dimensional submanifold. Yeah, so this infinite dimensional manifold, which consider things which cover extended by disks. If you intersect here, you get all our space and project to by isotropic things, you get exactly finite dimensional story. Yeah, so that was a construction. You use this quantization through ABCD tensors and get the quantization of this guy. Yeah, so it's do we really need foliation? I don't know. So the obvious conjecture is that different foliation gives the same story. You don't really need foliation. Yeah. And it's a big question. Why we need this quantization? What it says to us? It's not clear to me. Yeah, but it seems to be this kind of God-given object, and has this canonical quantization. What about resurgence?
Just before you go there, could I ask you, is there a geometric understanding of ABCD?
It's a really formal story because it's given by quadratic equation. It's kind of homogeneous situations. It's only one way to leave it to this situation. If you consider invariance of germ of a curve with tangency and foliation, this canonical coordinates here automatically. You get automatically nice coordinates x and y should be unique coordinates in which it's parabola. Yeah, so it's all this kind of very homogeneous situation, and there's really no choice to do anything. It's homogeneity. It's
because of the quadratic assumption.
Yeah.
Does this story give you any kind of a foliation of this big space moving B?
No.
Like a Lagrangian foliation?
No. Yeah. One can ask the following question: if you have just a Lagrangian manifold in affine space, does it have a canonical quantization? The answer is definitely no. There's no formula because this quantization should give, for example, a flat connection on the canonical square root of canonical bundle.
Right.
And if you try to write formulas, like for flat space will be zero connection to will be curved, there's no invariant expression which gives a canonical flat connection. Yeah, so it's something is really missing. It's kind of strange. From this geometry we cannot construct quantization, but it's come from moving curve. Then we have the whole story for free. Yeah, it's holomorphic anomalo equations. It's constructing the story. It's, so they explained you use this construction, but in the constructions from point of view of parameters, it's pretty strange.
That's the question.
Yeah.
Oh, so I just want to confirm your statement of conjecture. The conjecture is that this FG you constructed is independent
On foliation, on the choice of foliation. Yeah. It's kind of like symplectic invariance conjecture.
And another question. So how do you get back to finite dimensions from your infinite dimension?
No, you get infinite dimensional Lagrangian manifold in infinite dimensional affine space, but then they get linear affine coisotropic space. Because it's affine, you can canonically quantize it, and then get canonical Hamiltonian reduction to finite dimensional.
Why finite?
Because it's coisotropic, it's differ from a Lagrangian by finite number. It is exactly this first cohomology. If you mod out by orthogonal complement, you exactly get first cohomology of this guy. Yeah, so it's so there are a couple of things to say here. Parameters. If you want to see what are parameters, kind of what a normal form, and how normal form parameters of S omega containing your surface sigma, you consider like deformation theory. You get H tangent space to deformation will be H1 of sigma with coefficients in powers of tangent space to sigma m1, 2, 3. You get this subsequent terms on deformation theory by M Soda, and dual space. It will be kind of like product of this. So tangent space of deformation, some infinite dimensional space of this, and dual space. It's H0 of sigma And now consider cotangent bundle to power m, or maybe m plus 1, something like this. So it's sections of high powers of the sample line bundles. These are roughly parameters how all possible neighborhoods can look like, but parameters for my deformed Lagrangian manifolds, it's sequences of one forms, and one forms are really different guys. It's you get symmetric power of H0 sigma omega 1, and also add form power series parameter H bar. So you get much larger space. So this things maps this parameter space to this parameter space, which have kind of really different functional dimensions, like function of g plus 1 variables. Here g variables, and here it's 1 variable, yeah. And here it's functions of roughly maybe 2 variables, yeah. Yeah, so it's you get kind of very special families of Lagrangian manifolds and moving Lagrangian manifolds from the whole story. And about resurgence, this one thing, it's even the whole thing is kind of analytical neighborhood. One can extract some kind of sequences of numbers. For example, one gets this one forms. You can extend consider some value of this one form at some point, or integral one form from point to none, and get series in H bar. This series definitely should be divergent, and should be some factorial guy, but I'm pretty sure they are not resurgent, because to be resurgent, one can try to guess what are poles of Borel transform. Should be poles of Borel transform should be something like integrals of some disks on your symplectic surface with boundary on this guy. But because this guy is contractible, so there's nothing to consider. So the resurgence can appear if the surface is very big, like algebraic surface. Then one can hope for resurgence. Otherwise, it's something with factorial growth, but no analytic continuation. Okay, yeah. So that's whole story, which it was a reminder. And now I go to completely different business. Related to the following picture. I just recall you get B embedded to C to G, yeah, kind of, and you get variation of Hodge structures, yeah, Hodge structures. Then from this one can construct a complex integrable system. Namely, consider set of pairs point in B and point in Jacobian of your curve. And for Jacobian, you also can have version, consider line bundles of certain degree, not degree 0, but some degree 1, or I don't know what is good. And you consider map to the B, forget it's Jacobian. And fiber is abelian variety. So you get, and in fact it has also this holomorphic symplectic form. You get family of abelian varieties. You get classical integrable system. And again, in real life, if you put appropriate degree, you get some Hitchin system, stuff like this. Yeah. Then M is typically cotangent things to Bange, what people denote in Langlands. It's this whole stuff, and it maps to Hitchin base. So in this case, B will be CG in certain way, but so you get the story. And So what does it mean? On cotangent bundle to band J, you get a bunch of commuting Hamiltonians.
But do you mean really that you get that space?
Yes,
For a
exactly.
curve?
Yeah. You get commuting Hamiltonians, coordinates on.
So lots of fibers are not abelian riots.
Yes. You get a lot of commuting Hamiltonians, kind of polynomial functions with Poisson bracket equal to 0. And then you can imagine you put some Planck constant to get commuting differential operators. Okay, so we get some commuting differential operators, and now treat A over H bar as a formal parameter.
But for which group? Because
Jail group is jail in this case, for certain size, degree of covering of spectral curve or base curve, when it's cotangent bundle and so on, you get actual certain jail case.
because normally the dimension of the base is not G.
No, for jail, dimension of base is a genus spectral curve.
Yeah.
Otherwise, it's not the Jacobian.
Yeah.
So the spectral curve. Okay.
Genus of spectral curve. Yeah. Okay, but now consider the whole things over CH, and then because when you get H differential operators, you get on M, you have a sheaf of algebras over CH, which is isomorphic locally to this star product thing, and contains a sheaf of subalgebras, of commutative subalgebras. Commutative subalgebras, namely, it's the following. You consider functions constant along leaves and holomorphic on the base, pullback of OB. So you get sheaf of algebras and sheaf of subalgebras. And the story is the following. You have this sheaf of algebras and subalgebras. The claim that locally they look absolutely a unique way. Claim locally there are coordinates, and instead of Hamiltonians I will there are coordinates I and theta I, like momenta and on open parts, yeah, on all parts, the local coordinates, so that if you write this symplectic structure looks like this. The star product is usual Moyal product in these coordinates, and sheaf of subalgebras are functions of theta 1, theta g, and also at Planck constant. Yeah. So it's this things looks locally like this. And what is ambiguity? If you fix sheaf subalgebras, as ambiguity, you add to II certain II plus whatever AI of theta 1, theta g, AI theta 1, theta g, for all together it will be closed one form on theta 1, theta g, and you take form power series in h bar and maybe multiply by h bar, get high corrections. So just add differential of functions. The same story happens if you get formal family of integrable system. If you get formal family of classical integrable system, then you also get local coordinates, and ambiguity in vertical coordinates is just add derivative of function. So this kind of the same ambiguity is ambiguity for normal coordinates for classical, for family of classical integrable systems. Depending on small parameter. Yeah, this was observed some time ago, there was a paper by Mauricio Garay and Duke van Straten. They say, oh, it's wonderful. Of form power series, we cannot distinguish. There's no difference between classical integrable system and quantum integrable system. But there was a catch which kind of they missed one point. All of this true at points when there's no ramification. This is something in ramification you don't have. This picture. It's true outside of ramification. So what happens? What happens? This quantum integrable systems gives you a family of classical integrable system, but for M you remove ramification locus. You still map to B, and remove something of complex codimension 2. And when you remove something of codimension 2, something funny can happen. Like if you remove from C2 0, you can deform it in such a way that you cannot fill 0. You get infinitely many new parameters, so the things will be not fillable. And I want to say that one can control how it's not fillable in completely universal manner. Because besides this, you get again variation of host structure outside of the ramification divisor, but it has kind of different wrong behavior near ramification divisor. So to understand the whole story, we have to understand what's going on near ramification point for my integrable system.
So you remove something from B as well.
For B, remove something of codimension 1. No, for B, you don't remove anything.
What is the ramification divisor?
But image of ramification locus will be some divisor here. But you do, but I don't want to remove it here. Or maybe remove here. I don't know. It's
I do not understand.
Yeah.
So the ramification you remove what you have on the.
No, from B I don't remove anything. I have kind of, if I have something mapped to this, if I remove something, any subset is still mapped to B.
What is this ramification? What is? What's
No, B contains something called ramification.
in M? What is the
Points where this the derivative of the map is not surjection on level of tangent space.
Okay.
Yeah. And then a generic point of this ramification locus, the whole thing looks completely standard. How it looks like? It's actually reduced to one variable. We have kind of like M will be kind of C2. We get symplectic form dx dy, and map I. This is my kind of, and map will be from C. We have only one Hamiltonian, say xy goes to x cross y. One can write sum of squares, but like harmonic oscillator. Why so? We have function two variables. Suppose it has critical point and Morse critical point, and add constant to function will be eval equal to 0. And if interested in the function, it has some level sets, yeah, will be circles, and I get symplectic form. I get integral of omega over level sets h less than constant. And principal map to things maybe without coordinates, but I claim there's a canonical coordinate from A to the things if if consider area of h less than, let's say, r.
Put up some value somewhere.
No. I consider maybe real locus. Consider real chain whose boundary is h is equal to r.
Is xy is a complex number.
Complex numbers. I consider real two chain whose boundary lies in h is equal to r. I can fill a circle in hyperbola, and then this thing is equal to pi r. It's not up more or less, or maybe 2 pi I r. Yeah. So this knowing this thing, it gives you parameterization of the base in completely canonical way. Now this will be what this number r, whatever xi, maybe I denote by I now.
And you said real part, or you said h equal to something?
H equal to something.
H equal to k. Yes.
R, yeah, and consider circle like absolute value as x is equal to whatever x point I see to r, and half maybe y is equal to r half, something like this. Yeah, small small circle with story. And so this will be canonical coordinate here. Why it's canonical? The reason that you can see the it's now in pure classical situation, because I have function log x, and if you calculate the bracket, you get 1. And log x is defined up to 2 pi I under monodromy. Under monodromy it develops 2 pi I, and that's kind of characterizes I uniquely. It's such function, so there is another function which is under ramification goes at 2 pi I and has Poisson brackets equal to 1. And function is constant along the leaves here. It belongs to my commutative algebra. And also I2 minus log y is equal to 1. It's another function, another domain. Okay. So this and this I can have also interpret this integral over kind of loop. This circle is sitting loop sitting in level set, yeah, in level set of d minus 1 of omega of kind of x dy. If you integrate x dy, maybe take 2 pi I get this number I. So it's kind of like a cycle period of my two form. Now I want to calculate b cycle period. So b cycle period is, what is it? So I get my hyperbola, and now I can see the path connected point when y equal to 1 to point when x is equal to 1. Just make some arbitrary cuts and integrate my form y dx from x equal to 1 to y equal to 1, and path lies in I minus 1 of xy lies in hyperbola x I equal to this complex number I. And what I get I log I. If you integrate the stick, yeah. So it means that locally my this b sitting in whatever in C2 is kind of a period is I, and here it's b period is I log I, and my function of 0 here has this form. But here I made this kind of, it wasn't really actual integral of some cycle, I just cut it somewhere. And it's defined up to holomorphic expression. And here it's also up to holomorphic expression. Yeah, so we see the singularity of f0 up to holomorphic function is given by this I square over 2 times log I. Now go to main story. Now I go to quantization. What will be singularities of f0? One should calculate something, and it's really fun to do calculation here. Yeah, so so one can kind of recast what is log I. Log I. One can understand it in the following way. Before going to quantum calculation, one have two domains, kind of U1, which maps to C cross C star, and maybe you have U2 maps to C cross C star cross C, sitting in my C2 with xy coordinates. And on U1 you get, let's say, coordinates I is θ1, on U2 I and θ2. So I will be the same, but C1, C2 will be rotation coordinates, and it maps to, on U1, I θ1 goes to x is equal to I times exponent minus θ1, exponent plus theta1, and I theta2 goes to x equal to exponent minus theta2, I times e theta2. And then now we see that theta1 is equal to theta2 plus log I. Yeah, so we see that log I is interpreted as kind of difference of two coordinates on the common intersection. Okay, now we want to quantize it and repeat all the calculation.
Sorry, I can't quite read. So I1, theta1 goes to x, and then what is it? Oh, y is
Y equal to e c2, yeah, x, and y is equal to I times c2. Okay, so get this quantization. Now I want to do the same with quantum variables and repeat story. So now we have some quantum variables which commutated its h bar. So one can think it's multiplication by x, and y is h dy dx. I have coordinates of my guy. Now I have commutative algebra. It's generated by h bar and say y cross a and this guy. The claim, so it's this algebra. I claim first of all it has canonical element up to sheaf. Canonical element, which is yx up to shift. Add a kind of series in h bar maybe. Such that there exists another element which has developed monodromy 2 pi I and whose bracket is h bar. Namely, you make this very simple calculation. I claim that, for example, yx log x is equal to h bar. Let's do this calculation. It's very easy. It's equal to what? Y bar log x.
So when you say canonical,
It's canonical because in classical stories was elements such that there exists another element which function which goes under monodromy by 2 pi I and whose commutator is equal to and it goes up to 2 pi I. The story. Yeah. So it apply Leibniz rule. It's equal to sum of two commutants. Yeah. And then the following. It's commutator of h dy dx log x times x, plus 0 because this guy commute, and here you get h bar. Yeah, the same goes if you replace y value. Yeah, so it's kind of perfect. We get our canonical coordinate I. Now, what is the corollary of this? So I get my theta1 and theta2 are these given gadgets. Now I have immediately what is the difference between theta1 and theta2. I get these things commute. Yx log x bar plus log y bar is equal to 0. Because other commutator is minus h bar. So now what we do? I just repeat this procedure. See this. What was role of log of I? It was a difference of those two angles, and so this implies that log x hat plus log y hat is equal to certain function depending on h bar applied to y hat a hat. Because in this case, of 1 degree of freedom, if two things commute, one is function of another. So what is this function? Yeah, so the claim that this is kind of remarkable function of one variable depending on parameters, then we get this identity. So kind of find h fh. How we do? Now it will be kind of completely formal calculation, but which goes like this. We have the things x on function of x. Act on functions on x. And function I denote like x to power lambda minus 1, where lambda is some number.
so what the algebra
Algebra x, yeah.
this one.
Yeah, just to generators, yeah. Yeah, for example, what will be y bar, x bar applied to x to power lambda minus 1? It's equal h bar du dx times x applied to x to power lambda minus 1. Get lambda h bar times x to power lambda minus 1. So it's eigenvalue. So it's eigenfunction for this operator. Now apply what is log x hat plus log y hat applied to x to power lambda minus 1. The first one is very easy, so it will be, yeah, we should calculate this guy. What is log y hat applied to x to power lambda minus 1? We make Fourier transform. And Fourier I write kind of symbolically f of x go to integral of f of x exponent minus xi dx. Function Fourier f of xi. In this operation, x to power lambda minus 1 goes to what? Goes to gamma of lambda xi to power minus lambda. And du dx goes by multiplication by xi. Now we are ready to proceed. Log h bar over dx of x to power lambda minus 1 in Fourier transform is log h bar times plus log
So what is variable?
log of x du dx. Yeah. Du dx goes to xi, goes to log sum of logs multiplied by xi to power minus lambda. Okay. Now we can write this thing the following. It's log h bar plus gamma prime over gamma at lambda minus d lambda of exponent of xi minus lambda. Oh, times gamma of lambda, sorry. Yeah, because when I take derivative, you either get derivative of gamma or derivative of here, which gives you log psi. Yeah, so it's completely clean formula. Now we make inverse Fourier transform. You get log h bar plus gamma prime gamma of lambda minus du d lambda of what we have originally. What was x to power lambda inverse, lambda minus 1, and we take derivative, we get log lambda. So you take log h bar plus gamma prime over gamma of lambda minus log x to power lambda lambda minus 1. So we calculate this action of these things. You add log x, you cancel this story, and then you see that is equal to log h bar plus gamma prime over gamma at lambda x to power lambda minus 1. So it's again eigenvalue of the operator. And now we have from this identity, we know about this function. So the conclusion is that f h bar of lambda h bar is equal to log h bar plus gamma prime gamma over lambda. And then if you substitute the symptotic expansion of lambda, you see that f of f h bar of I is equal to log I minus h bar over 2I minus h bar square over 12I squared plus h4 124 and so on. So you get Bernoulli numbers, Stirling formula. Expand yeah, so you see that this guy before it has a logarithmic singularity, but now it has developed in higher order of H bar, developed poles of high order. And we know it's up to holomorphic function. And then if I try to analyze what is going on, I'll finish in 3 minutes. What is going on? We have this universal pole correction to function f0. And then f0 will be, it will replace in logarithm, it will be I times this log I, maybe f0 prime will be I log I plus blah blah blah, and then you integrate to get function of 0. Get kind of universal negative pole correction to the whole story. Just from classical harmonic oscillator, and I think it's my calculations new, so we already done it maybe 5 years ago, but I never published it. But it looks like a kind of fun, simple calculation with that sum of logarithm of canonical empirical is kind of logarithmic derivative of gamma function applied to the product. Yeah, this can be done in many different sense. But what is going on? So if we know kind of quantum flat coordinates, this I, we know this correction, and the whole kind of restrict, if it's kind of global integrable system, by global algebraic geometry, it restricts things kind of so uniquely that the claim that even this local flat coordinates, this coordinate I, which I use to reduce to standard harmonic oscillator things, is kind of restricted by global algebraic geometry, and it's different from topological recursion. Something else. It's something else, and it's pretty hard to get to the explicit calculation scheme, but it's really different from topological recursion. You get kind of maybe canonical from global constraints. Family of classical integrable systems, depending on this Ribach parameter, with such pole singularity at points. Now, so what it gives? If you stay now outside of this ramification point, you start to move your Lagrangian manifold. So first of all, you get from the story, because classical integrable systems, it's moving at the same as Lagrangian manifold in this symplectic vector space. We move this B sitting in C2G of more power series. So we gain. It's almost the same story which I say with my first part of the talk. When I choose splitter coordinates, I get quantization. But if I choose coordinates, it's the same as a moving Lagrangian manifold. The natural conjecture, which they are the same. As I learned, it's called Griffith's principle. I use it all my life. If two things kind of first approximation to the same, they should be the same, yeah? yeah, it's kind of a very general mathematical principle. It's called Philip Griffith's principle. But yeah, this should be the same. Then it will be some kind of meaning why we should quantize this bloody Lagrangian subspace in affine symplectic vector space. It's to make this comparison with this classical integrable system, which is very different story. And now finally relation to the story, because it's so rigid, it kind of...
So what's the claim that the quantization is the same?
In the quantization, when it's split by A and B coordinates, it was the same as moving on form power series your Lagrangian manifold B. And here also I move Lagrangian manifold B.
Where?
When I get quantization of integral system. Yeah, so it's.
Oh, I see. So the tangent, I mean the vertical direction.
Yes. Here the result of my story, because I identify quantum integral system with classical systems depending on parameters outside of ramification points. It means that I move this Lagrangian manifold when I stay outside of ramification points somewhere depending on H bar, and I moved on the first talk also.
You say that this Garayan von Straten can be extended, so it's true not on outside of ramification points. That's what you're saying.
No. The story was true outside of ramification points.
No, but you're saying the same thing. I do not say.
No, but I say that that's exactly 2.6. First, you can calculate it not doing quantum geometry at all, using this only classical algebraic geometry in this Bernoulli number story. It's the first time. But even without it, you get certain movement of this Lagrangian manifold. And my first part of the talk will also have a movement of Lagrangian manifold. And in the natural guess it should be the same. Why not? It's how many movements of Lagrange manifolds one can have. Yeah. Yeah, and maybe let's me start to finish, because this story is so restricted. We kind of know everything. We know kind of like how this near these flat points, kind of these flat coordinates move, and these flat coordinates. It's really very interesting because we have this canonical story. We choose a generator of my commutative algebra, so equivalent to the usual harmonic oscillator, and that means we control in H bar small eigenvalues of my integrable system. And this was this in this generator will be like usual h times half integer, h bar of half integer, and this was conjectured by Saint-Justin really long time ago, maybe about 25-30 years ago. About I think 30 years ago, he calculated on this. You get something like h over dx square plus whatever x square plus x to power 4, things like this. You look on small eigenvalues, and then you observe it in 4 power series, you get gamma function. Yeah, so I think it's still not proven, and my guess it's this picture will prove this whole story, and also has this resurgence for small eigenvalues, and it's things to understand here. Okay, thank you.
So questions?
So I do not see where discriminant on B is involved.
No, because you get this ramification of whole structure badly defined near discriminant.
Yes.
And this in this controls how this the badness of this behavior near discriminant.
Questions about can you apply this globally to Hitchin systems?
Yes. No, I think it's already this example. It's already a very good example to one can get to the final calculation without quantum geometry at all.
There is no chance to apply it to Hitchin because you use very simple singularities. I mean, it's just one-dimensional.
Of course, yeah, but in high dimension, generic point of discriminant set is this: you get splitting of coordinates. You get many stupid coordinates and just 2 coordinates when you get ramification.
So the first, the first degeneration.
Yeah, first degeneration. Yeah.
No, it's only near the generic point. Of the
Yes, but it's enough. It's enough. I already in codimension. I don't need codimension 3
Why?
by Hartog principle, because H1 I need only to know in codimension 2. If you disagree, we can talk later in some. Yeah.
And what happened to the non-conservative corrections?
Yes.
Recursion?
Yeah. No, I think this one can guess from other picture what are singularities of Borel transform. If it's the same story, it will be the same singularity. So the whole thing will be.
Is also conjecture which involves.
Yeah, Some has this also exponential small corrections, which he has very concrete examples, very concrete numbers. Yeah.
And what curve would this correspond to? I mean, which Hitchin system?
Okay.
Yeah,
You just change parameters on this guy. Yeah, you just add constant to get family of curves. That's it.
And it's
A family of elliptic curves.
family elliptical.
Plus, yeah, you consider y square plus x2 plus x4 equal to constant.
So
Yeah.
parabolic Higgs bundles on P1.
Yeah, we can translate it afterward. Yeah, it's irregular maybe. Yeah. Yeah.
Yes.
But thinking quantum mechanically,
Yeah.
go backwards. So you have discrete spectrum, which you like to
Yeah.
study from oscillators. But how about continuous spectrum?
Continuous spectrum. No. It's only for this discrete spectrum because it's a states concentrated near minima. Yeah. I don't know.
No real number.
Yeah, no, but you get 4 power series and some integer parameters, kind of like eigenvalues of harmonic oscillator.
But there is a continuous spectrum.
Yeah, okay. I don't want to think about
Any more questions? No?
Okay.
Thank you.